All right, we're back. We're on page 5 of Notes 14. We're talking about approximating definite integrals using summations. So like a right sum, a left sum, a midpoint sum, possibly a trapezoidal sum. So if you took math analysis, you are familiar with the concept of approximating areas using rectangles, because we do kind of a lot of it, and maybe you want to go back and review those notes. If you don't have the notes, at some point when I was out of my mind, I recorded all of those notes, and you could just watch them if you wanted to. So go, I don't know which notes, notes, I don't know, 17, 18, something like that. Go to the website, find what seems to apply, and give it a watch. But we're going to basically do that right now. So if we have, instead of a table of values, if we have a function, we can kind of essentially create our own table of values, or we can just look at a picture. So we have this function, and then what we want to do is we want to go from 0 to 10, and we want to try to like approximate the area. So what I've done is I've graphed it. GeoGebra, by the way, has an amazing built-in feature where it will draw these rectangles. So it's called rectangular sum. I'm going to play around with it at some point in the next, I don't know, at some point in these notes, I'll like be playing around with it. So you'll see it. It does a really good job. It can do right, left, midpoint, or like anything in between. You can do like 3/4 points. So like if you're starting at 0 and going to 1, the 3/4 point is at 0.75, and it will always put it 0.75 between the interval, like, 75% of the way from the start to the finish. It's crazy. It's amazing. Computers are really good at these things. And what we want to do is get really good at writing things that a computer or calculator can do. So what we're going to try to do here is approximate this area using 5 rectangles. You can see they are provided 1, 2, 3, 4, 5. And all right, so this it's going to be the definite integral from 0 to 10 of f of x dx is approximately. So each of them has a base of 2. And then what I'm going to do is I'm just going to, so we're using the right endpoints, right? So the first base is from 0 to 2. The right endpoint is 2. So I'm just going to say f of 2. And then for the next one, the base is from 2 to 4. The right endpoint is at 4. So I'm going to say f of 4. And I'm going to carry on f of 6. So even this is like an annoying amount of writing that maybe you don't want to do. Which, I mean, it's not bad. It's not too much writing. But you could write a summation for this. So what summation would you write? I would say that this is the sum from I equals 1 up to 5. So we're going from the first rectangle. This is rectangle 1, 2, 3, 4, 5. The first rectangle to the 5th rectangle. The base is always 2. And then the height is f of, so how can we say this? Well, what we're doing is we're starting at 0, and we're just gonna, to get to the first one, we add add the base once, right? So it's 0 plus 2. And then to get to here, we do 0 plus 2 times 2. And to get to here, we do 0 plus 3 times 2, and it's the third rectangle. To get here, we'll do 0 plus 1, 2, 3, 4 times 2. So really what we're doing is we're doing, if I represents the number of rectangle that we're currently working on, we're just doing 0 plus 2i. And so I'm going to switch to the calculator and let the calculator do both of those. Just like raked my nail. Wow. Raked my nail across the microphone. I don't know how that sounded, but then I went back for more. So let's, I apologize if that sounded horrible. Maybe it did. Who knows? I'm going to start a new document. The number one mistake that everyone makes on these is they forget to define the function. And if you don't define the function, the calculator doesn't know what you're doing. So like, it's not its fault that it gets it wrong. Okay. So the first thing I want to do is 2 times, and then I'm just going to do f of 2, f of 4, f of 6. You can see this is annoying. F of 8. And this is only 5. Like, we want to do hundreds or maybe thousands. I'll get 84. Yeah, 84. Okay. What if I type in the summation? So I'm going to go here, and then where are you? Summation from 1 rectangle to 5 rectangles. The first rectangle to the 5th is really what I'm doing. 2 times, and then f of 2i, really 0 plus 2i, but 2i. Enter 84. That's so much simpler. So we want to be doing that, but we got to get good at writing them. That's like one of our things. We're going to try to get really good at writing those. This, like, don't sleep on this. This is like a big idea. We need to be able to write these and eventually like work backwards from this weird summation to like, what definite integral could this be approximating, or what does it represent? So we want to be really good at understanding, like here 2, I'm saying that's the base. F of something is going to be the height, and then you can work from there. So get used to it. So here, all right, so now we're going to use 10. So we can do this the hard way. 0 to 10, f of x dx is approximately, so it's 1, and then it'll be f of 1, because it's a right sum, you don't use f of 0, you go f of 1, f of 2 plus, I'm gonna dot 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 this, plus f of 9 plus f of 10. Okay, so that's what we're doing. This to me is like a pretty obvious case of where we want to use a summation. So I'm gonna say that's a weird equal sign. Do it again. Here we go. The sum from one rectangle up to the 10th rectangle. So the first rectangle to the 10th. It's from the first to the 10th. Oh, and this is a right sum, right? So each of them has a base of 1 and then a height of f of 0 plus like 1 times I, which usually I try not to, it's so like, I'm so used to writing complex I that I put a little tail usually. Try to make them look different. I mean, there's kind of nothing you can do if you can't do it, but. So this should be more accurate. I mean, look at the 2 pictures. Like here, it's like we cut a lot of error out here versus here. And then here we cut out a lot of error that's there. We're just getting more accurate. The more you use, the more accurate it'll be. So let's go back to the calculator. And I guess I'll do, all right, 1 times f of 1 plus f of 2 plus f of 3 plus f. Boy, I wish there was a fast way to do this. I mean, right now I wish there was a fast way to do this that didn't, without using the summation. I don't know what that would be. F of 10. Enter. Okay, what? Control enter. We get that. Let's use the summation. So I equals 1 to 10, because 10 rectangles. 1. So where does 1 come from? 1 is really, you're starting at 0 and going to 10. So the distance between, so 10 minus 0 is 10. And you're doing 10 rectangles. So 10 divided by 10 is where you get 1. That's like similarly up here, where 2 comes from is you're going from 0 to 10, where you're doing 5 rectangles. So 10 minus 0 is 10, divided by 5 is 2. If we were doing 50, it would be 10 divided by 50. If we're doing 1,000, it's 10 divided by 1,000, and so on. Although yeah, okay, yes. And then f of 0 plus 1 times I, so just I. And there you go, 78.5. All right. So the logic is you'll get more accurate as you do more. So what I'm going to do is I'm going to start changing this up. I'm going to change this to 50. So the next one in the notes is 50. So we're going from 0 to 10 on the x-axis, and we want to divide it up into 50 equal base rectangles. So our delta x is going to be 10 divided by 50. We're cutting the x distance into 50 equal pieces. So 10 divided by 50. And then for this, we want to start at 0. And then we just want to add the base of the rectangle. So 10 over 50 times the number of the rectangle that we're on, right? For the first rectangle, you add the base once to get to the right endpoint. For the second one, you add the base twice to get to the right endpoint, and so on. So let's see what this gives us. All right, 74.34. It's a smaller number. It's closer. It's more accurate. Let me do like 1,000. So 1,000. So we want to make 1,000 equal slices, and then each of them you have to like keep moving 1,000. So 73.3834. Let's see what the calculator says the definite integral is, because the calculator can do those. Let's go 0 to 10, f of x dx. 73.333. What if we had done 5,000? I don't know why. I just love doing this, like changing it up and seeing what happens. It's like, how many do we need to do to get close enough? I mean, that's, I don't know. 5,000 isn't really as close as I'd like to be, but it's pretty close. Okay, so that's the idea. We want to get really good at that. Let's go back to the notes just to make sure everybody's on the same page, which how could you not be at this point, but like whatever. Do it. Go back. Okay. So we did it. We wrote some summations. Writing summations is going to be kind of a big deal. It's not like the hugest thing in the world, but like, look at this picture, man. When we use 50, so much more accurate. When we use 1,000, I bet you can't really tell the difference. 5,000, you probably can't tell it at all, like with the naked eye, but we saw the decimal is still off by a lot from a calculus standpoint, not really a lot from like a giant number standpoint. Anyway, this is kind of a preview of what we're gonna do when we have a function. So I'll be back in the next video and we will do some more. So I will see you there.